G'day guys, our group is myself, Seamus, Alfred and Harrison, and our topic is the removal and fate of emerging pollutants in municipal wastewater treatments. So wastewater originates from predominantly industrial, commercial and domestic sources, and in the majority of cases this effluent's released back in the environment after receiving lengthy processing and management to minimise its impact on the health and safety of the environment and the public. However, with the development of new technologies, newer emerging pollutants are being detected and researched. These can be originating from a new source, using a different or newly exposed pathway to the environment, a waste or byproduct from a new treatment process, or a new detection method has highlighted their existence. Currently, the baseline data, including occurrence and concentrations of management policies and processes to deal with most of these emerging pollutants, do not exist, and their ultimate fate is largely unknown. A study conducted of marine water from 30 sites adjacent to stormwater outlets across the entire Sydney estuary, the first of such in Australia, had alarming results. The presence of recognised domestic waste markers and pharmaceuticals in all parts of the estuary, especially after a long dry period, indicated that sewage is leaking into stormwater systems or domestic wastewater is being illegally connected into stormwater piping. Irregardless of the stringent treatment protocols for the processing and fate of our wastewater, all pollutants will never be completely removed from reaching our environment if this is the case.
Aerobic and anaerobic water treatment. Aerobic is done especially when COD is below 2000 milligram per liter and when the production of effluent quality is 120 milligram per liter and 20 milligram per liter of BOD. It is technological very good as it improves oxygen supply in the water, decrease of sludge, work within the integrity of control system. The anaerobic is the opposite when the COD is above 2000 milligram per liter and BOD is above 1000 milligram per liter. This option is more sustainable and in the long run more economical. There are good options for this anaerobic system. It produces biogas, low sludge production, no odor release, small footprint, and more energy production instead of energy consumption.
A membrane is a thin, porous sheet that separates impurities from water. A ceramic membrane filtration system uses a unique ceramic membrane to remove micropollutants, turbidity, harmful bacteria, and protozoa that may impart the taste, colour, or odour of water. Advantages of the ceramic membrane filtration system include low operation cost, high water recovery rate, and chemical, mechanical, and thermal stability. The ceramic membrane filter is an asymmetric bundle of ceramic membrane channels housed together in a high-density membrane packing. Different pore sizes can be used in the process to cover a size range of 5 mm down to 1000 Daltons. The ceramic nature of the membrane allows it to handle extremes in temperature, acidity, and pressure without concern. The ceramic membrane filter uses a cross-flow filtration system. The osmotic pressure difference either side of the membrane causes filtrate to be drawn out through the membrane. The filtrate separates from the medium and passes through the membrane, while rejected particles are swept away through the feed flow.
Constructed wetlands are designed to take advantage of natural forces to purify wastewater. These include photolysis, plant uptake, degradation, and soil absorption. Horizontal subsurface flow constructed wetlands contain an impermeable layer at the base with porous filtration media at the inlet and outlet and a soil bed in between with planted vegetation. The simple system has many benefits. Surrounding the plant roots and rhizomes, a network of anoxic, aerobic, and anaerobic conditions exist. Some conditions are more effective at removing certain pollutants. For example, within pharmaceuticals, anoxic removes halogens, anaerobic removes diclofenac acid, and aerobic removes ibuprofen. Comparing the ESD between conventional wastewater treatments and constructed wetlands using a triple bottom line approach. Environmentally, constructed wetlands are proven to be much more effective and efficient at removing CECs. They also generate new diverse ecosystems and they also use very low energy and chemical consumption. Economically, Initial costs are similar between the two. However, maintenance and operations costs are much lower for wetlands. Socially, they are much more aesthetically pleasing to the eye and improve public safety. In conclusion, further exploration and research should be done into the implementation on a widespread scale, especially in regards to removing contaminants of emerging concern.